So what we will do here is to add a new entry that allows ICMP packet to be forwarded to table 1, right? So how we do that, we go back to the notes, and from the notes we see that we can go to uh, the browser and add this match fields. So ether type has to be 0800. The protocol is 1, so ICMP is protocol 1 among the IP version 4 protocols, or it's encapsulated inside IP version 4 and it has protocol 1. And priority 200, so make sure that the priority is higher than the existing entry, which the highest one is right now is 100, and the instruction is send it to table 1. Right? So we will do that and we'll see how the switch reacts. So we'll go back to our browser and we'll go to flow control, and we make sure that we are actually working on table 1. Flow operation is add, and match fields, so we want to match the ether type. So you can start typing ether type, you narrow the search, and then you can enter the hexadecimal number here and add another field to add the protocol, IP protocol, and protocol 1. Then make sure that the priority is 200. Don't worry about the timeout and the other fields. This is permanent. If I don't put any timeout, the flow entry will be permanent. And the action, actually the go-to table is here, so we just need to make sure that the number is 1. So there are 5 instructions. One of them is go table. Okay, so that's everything that we need to enter. Everything else is default. Click submit. You see the message here, message sent successfully. If you go back to the flow, you'll see that we added a new entry here. Okay, so now we told the switch that ICMP packets are allowed to continue to table 1. Let's go back to our terminal and see if ping works this time. And ping works. Okay, while ping works, let's go back to the browser and see what happens. So now before we saw these entries at the bottom because we are allowed the switch to learn these entries, but now these packets, ICMP packets, are allowed as well. So when the ICMP packet come and matches this entry, goes to this one and gets forwarded, right? You'll see here that as long as I am sending IP packets, this byte count and packet count is increasing. It's now 104, 112, and so on. Okay, so that's how I created my access list using flow entries. Before I move on, if somebody has a keen eye, they will notice that the bottom entry here has priority 100, while when I explained before, I said priority is 0. Well, it doesn't matter as long as this any has the lowest priority, but it should be 0 really. So I need to go and update my code and make sure it is 0. Or you can update it yourself. Go change it if you want. But yeah, this is one of the things that I noticed just now. Um, this is our topology, so we are communicating between 3 and 4. What happened to 1 and 2? Well, the switch doesn't know about them right now, and the controller doesn't know about them either. So what I'm going to do here, if you see the nodes, you see you are supposed to do ping all. So let's go and do ping all. I'm going back to the terminal and I'm going to stop this and do ping all, which is Mininet way of making sure that every node pings every other node. So it was successful, which means we were allowed to ping all of them. If we refresh here, we have the full topology. If we go to the flows, look at this. Now, because we have 4 hosts, each one of them needs to contact the other 3. So we have how many? 4 multiplied by 3, 12 divided by 2, or actually, and both directions, so we have 12 entries. You count down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 entries. For each direction, we need entry. Right? Now, having said that, you notice that this is not really um, an efficient way to forward packets because now we need n multiplied by n minus 1 entries for n number of nodes. So in the design course, we'll find how to do things better than this. So I'll keep you excited until you get to the design course. But this is the simplest way we can do switching at layer 2. The last thing I want to do is save the configuration. So it will save to your local machine. You can take a look at it if you want. It's in JSON format. Um, Now I realized again that I didn't show you the. So this is the topology. Sorry again, I didn't switch the screens. So this is the topology, as I was saying. This is the flows, and I was now they disappeared because they expire. So if I do ping again, I'm not going to show you the ping, but if I do ping again, you see here 12 entries. Um, so 12 entries, as I said, not an efficient way to do forwarding, but we will see that in the design course. So uh, what else did I miss showing you? I did the configuration, so I'll save the configuration here. You will see it at the bottom, so it will save it in your uh, download folder in your local machine. Okay, so let's go further. Now I want to restrict ICMP before I allowed ICMP to go anywhere. Now I want to restrict it a little bit. So that I allow packets here says above task allow ICMP traffic to pass freely. I want to restrict ICMP traffic by allowing only ping to and from host 4, right? So I want just any ping that goes to host 4 or back. Anything else should not be allowed. So what I want to do is modify my previous entries. So I'm going to delete the entry that I just entered, and I want to add these entries. So um, let's see. I'm going to switch back to the browser and go to the flows click on the 200 here, this entry, and delete it, and go to the flow control and add ether type. So these matching fields, ether type 0x0800, protocol IP protocol, and then number 1, priority 200. Actually, and I'm missing one field here, which is the IP version 4 source is, so this is the source IP address. So this is 10.1.1.40. This is the IP address for host 4, priority 200, and then this I want to send to table 1. Click on this, message sent successfully. So before you move on, we're gonna use the second entry here, which is same as the previous one, except now the destination is 10.1.1.40, right? So I'm not gonna change anything except this field. I'm going to change it from source to destination. Submit, and let's go to the flows and see what happens. So these two entries that I just added, same priority, ether type, it displays in decimal. I entered it in hexadecimal, but it displays in decimal. So 2048 is ether type for IP version 4. The source is 10.1.1.40, and the protocol is ICMP, and here is the same thing, and the destination is this. So in both cases, send to table 1. What if they don't match? Then they will just be dropped. So let's go back to the terminal and try our theory here and see if this works. So let's ping between host 1 and host 4. It should work, okay? And because ping is bidirectional, so we know that ping, the echo and echo reply are successful. Go to the browser and see, you'll see here the number of counts increased and the number of bytes increased. So packets increased and bytes increased. So we know that we did something right here. All right, let's try to ping between host 1 and host 2. Ping won't work because it's not allowed. Okay, just last time to confirm, let's ping between host 3 and 4. Works. All right, so ping, if I do between host 4 and host 1, sure, 4 works fine. So I am allowing ping only to and from host 4, but not any other hosts. Okay, let's see what else. Now, if you look at what we did, back to the browser, and save the configuration just so that if you make a mistake, you can go back and restore it. So to restore, just find your file that you just saved and then click restore. If you look at the flows, you see that I entered everything manually, which is not convenient if I am doing this for a complicated access list. So we want to go back to something that we are familiar with. We want to write these instructions in a file and then load that file. So we want to do something similar to what we studied in the class. Write the access list in the format that we discussed. ICMP is the protocol, then the source IP, the source port, the destination IP, destination port, and then either permit or deny. So there is a deny all assumed at the end, so I'm not going to write it here, but let's take this and convert it into a file. So we are supposed to create this in a file called acl.csv, and then we're gonna use a different application this time. Our application, the original application, it accepts command from the GUI. The new application is called ACL file. This accepts the access list from the file itself. So we'll go to the terminal. We'll go to the other terminal. This is the controller terminal. Let's stop the controller and let's write down, make sure that I don't have it already. Okay, I don't have it. So let's write down or create this file. So it's acl.csv, and then you can copy and paste if you want. Let's save it. Control X. Yes. Okay, and I am going to start the controller again, but not the old code. The application is another application. Okay, everything looks good. Let's go to the browser and see what happened. Let's refresh. So here we see that as before, the default entry here that the controller enters or the application enters is any, match any, send to the controller. Here is slightly different because we added those access lists in the file. So the first thing that we saw, the default is drop everything, drop any. Then we have this ARP that was there before, so allows ARP, and then allows any network or any node in network 10.1.1.0 to go to 40, and vice versa. If I want to send ping from 40 to any node in the network, then it's allowed to. So this is the implementation of these two access lists. That's different from what we did before, right? What we did before, we just specified the destination. We said if the source is this one, allow, and if the destination is this one, allow. But now here we see it's more restrictive. We specify the source, so this is more restrictive, and this is better performance. The previous one, or better security, I should say. The previous one was the equivalent to from any source to destination 40 allow, and from 40 to any destination allow, right? Here is, we specified the access list to be more restrictive. and more restrictive is better, as we discussed in the lecture. So now I am allowing, if this is my server, I am allowing the traffic or the ping to go from the server to my local network and vice versa. Okay, let's test. So we'll go to our Mininet terminal again and ping or ping from host 1 to host 40. Works fine. From host 3 or 2 to host 4, that's fine. And if I ping between host 1 to host 3, it won't work. How about I ping from host 4 to 8.8.8.8? It won't work either, right? So let's see. Now we did the testing that we were supposed to do, the questions and deliverable. Observe the entries in the switch table and compare them with task 3. I just mentioned that. Compare the Python code. Well, let's look at the code. So let's go back to one of the terminals here. Let's take a look at the code. I won't have time to go over it bit by bit, but let's take a look. So I stopped my controller, Control C, and let's use nano and SDN, and the first one is the learn switch and ACL. So I'll go over the steps very quickly. So here we define the priorities, and then this is the switch, this switch features handler. It's the method that initiates the switch. It adds the default or the initial entries. You will see here, if you look at the comments, you see that I entered flow entry in the ACL table, which is table 0, and I added the table miss entry, which is the last entry in table 1, the forwarding table. And this is the method packet in handler. This is the method that handles any packets that the switch send to the controller. So here, what did I say before? It will get the port, get the packet, the source and destination, and it will enter them into the MAC table. Here is the line that takes the MAC table and enters, updates the MAC table. For each source MAC, it will assign, it's a dictionary in Python, so the source MAC itself is the keyword, and the input port where the packet comes from is the value, right? And then it looks at, if it tries to find the output port. If it finds it in the MAC table, then it will add an entry. If it doesn't find the output port, it will replace it with a flood. It says this is the output port. We'll call it later the reserved keyword for flood, right? So it will send a packet out that says flood the packet. So that's simply the code that does the layer 2 switching. Everything else has to be entered manually. If I look at the other file, we'll see the same thing here, with the exception that now it reads the file that we created, acl.csv. It reads it, and then based on that, it will add entries in this method, the switch features handler, it will read the file and it will add those entries. So for every rule in the rules table, or the rules list in this case, um, create a message flow entry and send it to the switch. Here we want to make sure that the steps, we start from 800 and start decrementing, so every step, let me go back to the access list and show you what I mean. So I want to make sure that um, the top entry is matched early, so uh, I will give it a higher priority, right? So in order to prevent a situation where the packet may match two entries at the same time, so I want to give the top one higher priority so it is executed, right, rather than the other one. So this is the numbering here, the priority here in implementing this access list using OpenFlow is very important, because unlike normal access list in a firewall or a switch, um, it's not match from the top and apply the first match rule. No, it may match multiple. So in order to simulate match the first one, then we have to give the top one higher priority. Okay, so other than that, um, the rest is the same as before. Here this is just to simplify. So if I read ARP in the file, it will translate it into a protocol number, because OpenFlow doesn't understand the keyword ARP, so I have to translate it into the number. So when I see ARP in the access list, it will change it to um, ether type ARP, and for LLDP it will change it to these keywords for OpenFlow, or these numbers for OpenFlow. Okay, so take a look at this. And by the way, this rather than writing the whole code from scratch, it's actually it it inherits the other one, right? So the learning switch ACL file inherits the learning switch ACL. So there are methods that came from the other file, so I don't have the packet N, for example, the packet N handler. I don't have it here because it was inherited from the other file. So all of these are things that added to the ACL file. Okay, what else remain in the assignment? So task 5, we want to allow HTTP traffic. So HTTP traffic, stop the controller, modify the ACL.csv file, then run the controller and application again. Note that unlike any ACL, there's something missing here, so maybe I need to there's a message, there is a sentence that's missing here. Okay, hopefully by the time you get the assignment this will be fixed. What I want to do here is to modify the access list and then try to send traffic using TCP. Now if I do this it won't work because TCP is not allowed, so we need to allow it. So let's go back and modify that file to allow TCP. Okay, so let's see. I am starting this file, and then I want TCP allowed from any host in the network. The source can be any to 10.1.1.40/32. I don't think you need to do /32, but anyways, you can leave it. Port 80 and permit. So that will allow traffic to go from any node to the server. And to make sure that we allow the, the traffic from the other direction, so what we need to do is create another entry um, that says traffic from 40 port 80 to go to any node. Since we don't know what the source port is, the source port can be anything, so I'm just gonna leave it any. Let's order it. Doesn't matter the order, but I like it this way, so it matches the ICMP. And let's save this and run the controller again. Let's see the browser and see if everything is good. We see here that we allowed TCP, so protocol 6, that's TCP. Here it shows UDP destination, just ignore it. It's a bug, but this is the port TCP, so the port here is obviously TCP port 80, and here it works fine. So it works in some case in the destination, but it won't work in the source for some reason. Everything else is as before, so these two entries 780 and 770 allow ICMP, and 760 here allow ARP, and then the deny all. Notice here that we don't have a default mechanism uh, to do established traffic or the traffic in bidirectional. So this is an implementation of a simple packet filter, right? So this is not an implementation of stateful packet filter that we talked about in the lectures. So this is implementation of simple packet filter. If we go back to the notes, so we can test by trying to send traffic over TCP using NC tool here. So what we will send, we'll send traffic um, from a node to the server, and we'll make the server save the data in a file. So let's go back to the terminal, Mininet terminal, and this is an extra step just in case somebody else left the file open or left. So we're gonna remove the file if there is one exists. There is usually there isn't, but we'll just remove it. So if you get an error that says cannot remove, just ignore it. Just in case you did this multiple times, so you want to remove the old file, and then start the server by using this NC tool. This command will listen, so the -L is for listening to port 80, and any data received is sent to the output file, and then the ampersand here just to make it work in the background, so we can use the command line to send traffic from host 1. So host 1 use the same tool to send traffic to H4 on port 80, right? Enter, and you can say hello server. Make sure you click enter. If you want to add um, any other text, go ahead. From me, and then Control C. Now let's go to the browser and see if there is traffic going. TCP traffic, there is few packets passed, so there is traffic allowed to these two entries. Let's go back to the terminal and see if the server actually saved anything in the file. So let's go h4 cat out.file. Yes, so anything, the things that I sent were received by h4 and they were saved, so everything works fine. Let's try different port and see. I'm gonna do the same thing, but instead of 80 I'm going to do 8080. Let's remove the file before we do that, so remove the output file. Okay, removed it, and then run this, and then we'll send traffic to port 8080 and see what happens. Hello server, remember oops, I cannot go back, delete backspace, but anyway, so let's enter Control C. There is nothing in the file, so no traffic went from host 1 to host 4. Let's go back to the browser. No increase in packets here, so still 6 and 4 as before. So why? Well, obviously because I'm passing traffic. I'm allowing only port 80. Port 8080 is not allowed, so eventually it will not match any entry and it will be dropped at the bottom here, right? So everything is working as expected. So once you do this, submit your acl.csv file. I think I gave you all the answer, didn't I? And you can save the configuration. Go to the configuration. Make sure that this is formatted. Click and save. If you want to take a look at the file, let's open. I cannot open it with that, so the file, I'll let you see it yourselves, but the file is written in JSON. So if you look at these files, you will find them that if you don't do formatted, they will be all lumped together. But if you see formatted, you see indentation, so you can take a look. What else? The SDN controller and application must be restarted every time we need to modify the ACL. This is not practical in production network. Using your knowledge of Python programming, suggest ways to improve the application so that ACL can be modified without restarting the controller application. Okay, so now I want you to do this. I don't have the answer, or maybe I have few answers, but I want you to suggest few things, especially those who are probably have more expertise in programming. So how can I modify the access list without restarting the application? I'll let you come up with ideas. That concludes the lab. Hopefully it was useful and informative. If you have any questions, let me know, or any of the instructors, and we'll see you in the next lab. Thank you.